Hey guys, so I'm going to just walk you through this Exam 4 Worksheet 2 supplement, and it's basically just a summary of all the nucleophilic substitution reactions. So on your blank copy, please fill in these words or phrases that are in red. Okay, so let's start. Question 1, nucleophilic substitution versus beta elimination. Fill in the blanks with the appropriate words to complete the sentences. So there are basically two different types of reactions that you're going to see in Chapter 9. There are the nucleophilic substitution reactions and then the beta elimination reactions. And they're actually very similar to one another, so that's why students get confused on what they are. So I'm going to distinguish between the two below. So, a nucleophilic substitution reaction refers to any reaction where an electron-rich nucleophile replaces a leaving group. That makes sense? We are substituting this leaving group with a nucleophile. That's why it's nucleophilic substitution. Next, beta elimination refers to any reaction where an electron-rich nucleophile removes a hydrogen from the beta position and donates its electron density, forming a double bond, generating the removal of a leaving group. I know that might sound really confusing, but it'll make sense in the graphic that we have described over here below. Okay, so both reactions involve nucleophiles, so what's the difference between a nucleophilic substitution reaction or a beta elimination reaction? Well, actually, they're very, very similar. So look over here. This is a nucleophile acting as a Lewis base, and this is a nucleophile acting as a Bronsted-Lowry base. So recall that nucleophiles are basic species, but they can have different properties based on the type of reaction that we're promoting. So the one on the left, where we say it's a Lewis base, this would promote one type of reaction, and the nucleophile on the right, which is a Bronsted-Lowry base, is going to promote a different type of reaction. So a Lewis base is a lone pair donor. So this nucleophile donates a lone pair, forming a nucleophile electron bond, while also removing the leaving group. So if we look over here, we have this nucleophile. This nucleophile is going to attack this partially positive reactive carbon and facilitate the removal of that bromine leaving group. Okay, so that's what it's just saying up here. This has a lone pair donor, so it gives off a lone pair to form an electrophile-nucleophile bond while also kicking off that leaving group. Okay, so this is what happens if your nucleophile acts as a Lewis base. All right, now look at this one. A Bronsted-Lowry base is a proton acceptor. So this type of nucleophile will abstract a proton from the beta position, donate the remaining electron density to form a pi bond, and then remove the leaving group. So this is what we said above, what a beta elimination reaction was. So this is going to make more sense now when I show you the diagram. So this nucleophile will remove that proton. Remember, Bronsted-Lowry bases like protons, so they take the proton, donate that sigma bond density into the ring to form a pi bond while also kicking off that bromine as a leaving group. So I want you guys to notice something really important. Note that we use the same reagent and the same nucleophile with both reactions, however we get very different products. So look, over here we have this nucleophile and we also have this nucleophile on the right. Likewise, we have this same reagent on the left and this same reagent on the right, but we clearly get two different products. Okay, so that's this whole concept of this entire chapter. We have these reagents and these nucleophiles, and they all might look similar, but based on the conditions that we are in, we can promote different types of products or different types of reactions to follow. Okay, so the difference between a nucleophilic substitution reaction and a beta elimination reaction should now be clear. Nucleophilic substitution is the nucleophile actually attacking and forming a nucleophile-electrophile bond, which we see over here, while a beta elimination reaction actually has this nucleophile take off a proton, form a double bond, and then kick off the leaving group. Okay, that's beta elimination. You're eliminating via the beta position. So if you want to know why we have a beta position, the alpha carbon is that reactive carbon where the halogen is attached to, and the beta position is just one carbon removed. So it's beta elimination, which causes that leaving group to go away. Are we clear on that? All right, so why do we get these different products? So there are two different types of nucleophilic reactions. So now we're only going to focus for the rest of this video on nucleophiles acting as Lewis bases, so just this left diagram. And there are two different types of those. So there is the SN2s and the SN1s. So these boxes are all blank on your worksheet, so feel free to pause the video and fill in the information depicted below. All right, so the definition of an SN2 reaction. So bond breaking and bond forming occur simultaneously, and departure of the leaving group is facilitated by the incoming nucleophile. All right, so let's break those words down. Bond breaking and bond forming occur at the same time, okay? So that means when that nucleophile comes in, we're going to form a bond, but at the same time, we're going to break a bond, which means kick off that leaving group. okay? And this only happens when the nucleophile is present. So let's just look at this picture again. This nucleophile comes in, forms a bond, while also breaking that bromine bond. Okay, so that's what it means by bond breaking and bond forming at the same time. And this only happens, obviously, when this nucleophile is present. Okay? That's an SN2 reaction. An SN1 reaction is basically when a bond breaks between the carbon before the nucleophile even approaches. So if we look at this diagram, I didn't show an SN1 reaction, but this bromine would be kicked off by itself, okay? And you would form a carbocation. And there would not be any nucleophile present. It just kind of happens on its own. The bromine is capable of just leaving on its own, forming a carbocation without the nucleophile present. Okay, that's an SN1. So those are the two differences. In SN2, the nucleophile is required to kick off the bromine, where in SN1, the nucleophile is not required to kick off the bromine. All right, kinetics. So remember this back into Chem 2, we talked about kinetics, so this is all about the rates of reactions. So an SN2 reaction occurs in a single-step concerted mechanism where the nucleophile attacks another molecule. All right, so again, we said this nucleophile is going to attack in a single-step concerted mechanism. So remember, we see the two arrows happening at once. That's concerted. And the rate-determining step is therefore dependent on the presence of both species. So we need this nucleophile and we need this reagent present to promote an SN2 reaction. So the rate law would kind of look like this. Rate equals some sort of rate constant K, dependent on the nucleophile and the reagent concentrations. So if you wonder why we have the number 2 after an SN, that just means bimolecular. So there's a nucleophile and a reagent. Those are two species, hence bimolecular. So it's a nucleophilic substitution reaction. More specifically, it's bimolecular. So you need that nucleophile and you need that reagent. Now comparing it to an SN1 reaction. For an SN1 reaction, the rate determining step is the removal of the leaving group without the nucleophile even being present in the first place. Okay, so this is a unimolecular reaction. So I didn't draw out an SN1 reaction, but you can imagine in your head that we have this bromine just getting kicked off by itself. Okay, so that's the rate determining step. However long it takes for that bromine to come off will dictate how long this reaction progresses. So this bromine can just come off, that's the rate determining step. But again, we didn't need that nucleophile to do that. Remember, it just kind of comes off by itself. So this is why it's unimolecular. The rate law is only dependent on just that molecule in the beginning, that reagent. Okay? Is that kind of clear on kinetics? So the next thing we want to do is talk about stereochemistry. So for an SN2 reaction, remember, we need that nucleophile to come in and attack. But it can only attack from one face. So if, let's say I have that bromine on a wedge, or a bromine on a dash. That nucleophile can only come in from the opposite direction. So if the bromine is on a wedge, the nucleophile is going to have to come in on a dash. Or if the bromine's on a dash, the nucleophile is going to come in on a wedge. Okay? So you can see how in SN2 reactions we need backside attack. So what happens is we have inversion of the stereocenter. So let's say I started with a wedge, your final answer is going to be a dash. If I started with a dash, my final answer is going to be with a wedge. I hope that makes sense. All right, for an SN1 reaction, the leaving group departs by itself, remember. So remember that bromine picture before? That bromine just comes off. We form a carbocation species. Well, this entire semester we've been talking about carbocations and what happens when we go through a carbocation intermediate. Well, we actually have racemization, which is just a form of enantiomers, and we have this racemic mixture forming because remember that planar sp2 unhybridized carbocation can be attacked either from the front face of the p orbital or the back face of the p orbital, and that's why we have a mixture of enantiomers. So in an SN2 reaction, we'd expect exclusively one configuration of a molecule, more specifically the opposite configuration of what we started with, and in an SN1 reaction, we would expect both enantiomers to form because we go through that carbocation intermediate. So those are some key differences in stereochemistry. All right, other considerations. So in an SN2 reaction, we are governed by steric factors. That is, can this nucleophile approach the reactive carbon, or is it hindered by substituents? Okay, I know that may not make sense right now. It will make sense later in the video, but just bear with me here. SN2 reactions are governed by steric factors. So are there other methyl groups, isopropyl, any bulky groups attached to that carbon that may limit this nucleophile from approaching from the backside? That's what we should be thinking. In an SN1 reaction, we also want to consider electronic factors. So remember, we're going through that carbocation intermediate. So again, we want to think about carbocation stability. We've done this all semester. So what you should consider is, do I have a sufficiently stable carbocation to allow for nucleophilic attack? All right? I know that's a lot of information, but we're going to do question 3 and we're going to piece it all together. And it's just this tiny little graphic that will do it for you. So we have basically 4 types of molecules that you can see: a methyl, a primary, or a secondary, or a tertiary. All right, so I want you to be careful and actually distinguish between what would promote which reaction. So if we look at this arrow at the top, we start at the secondary and we go towards the tertiary position. Increased carbocation stability prefers SN1 reactions. So that makes sense. If we were to remove this halogen, on its own, remember it does that, that's the rate determining step in an SN1 reaction, it will just come off. We form a carbocation, which is stabilized via hyperconjugation via R1 and R2. Remember that donates some electron density into that electron deficient carbon. Likewise, in this tertiary species, if we were to get rid of this halogen, on its own, the rate determining step, we'd form a tertiary carbocation, which is stabilized via hyperconjugation via 3 adjacent alkyl groups, okay? So these are very stabilized carbocation species. That's why we would see an SN1 reaction. So if you were to see this on the predict the product section, if you saw some sort of secondary or tertiary molecule, you'd start to think SN1, all right? So decreased steric hindrance promotes SN2 reactions. So we're starting at the secondary and we're going to the methyl. You can see, remember, we talked about steric hindrance for considerations for SN2 reactions, and as you go to the left of this arrow, you see that we're getting less and less bulky. So we're consistently removing R groups as we go along, which makes it easier for this nucleophile to attack and replace the leaving group. I hope that makes sense. All right, so why do I have this secondary structure in pink? Well, you can see that these 2 arrows overlap with one another. So we have to kind of consider some other things because we have this overlap here of an SN1 and SN2. A secondary molecule like this can actually promote either or. So what should we do? Well, first we want to consider the type of nucleophile. So if I have a strong nucleophile, remember we need strong nucleophiles for backside attack, that would be an SN2 reaction. So strong nucleophile, immediate, and if I see a strong nucleophile and a secondary molecule, I'd immediately think SN2. If I saw a weak nucleophile and a secondary molecule, I'd probably think SN1. The next thing I should consider is the type of solvent that we have. So we either have a polar protic solvent, like water, alcohol, carboxylic acid, so those are capable of actually protonating things, or we have polar aprotic solvents, like acetone, acetonitrile, THF, DMF, DMSO. Those are not capable of protonating things. So if we have a polar protic solvent and a secondary species, we'd probably think an SN1 reaction, and if we had a polar aprotic solvent, we'd probably think SN2 reaction. And the reason that is an SN2 reaction, remember, does not go through any electronic carbocation intermediate, so we don't need a polar protic solvent. We would need a polar aprotic solvent to prevent us going through that carbocation intermediate. So I hope that makes sense on why we do a polar protic solvent versus a polar aprotic solvent. Likewise, an SN1 reaction would go through an electronic carbocation intermediate, so we would need this polar protic solvent to kind of keep those 2 reagents separate, the nucleophile and the positive carbocation. Okay, so it's very important that you get all of the basics down before you come to office hours on Friday. This is supposed to be a supplement to kind of help figure everything out, because what we're going to do in class is we're just going to give you a whole bunch of examples of different types of predict the product questions, and you need to tell us, is this an SN1, is this an SN2, and we're just going to do that the entire time. All right, I hope this kind of helps clarify. Email me as always with any questions. Good luck studying, guys.